Hello everyone, my name is Qinyi Li. I'm from Griffith University, Australia. Today I'm going to present a simple and efficient CCA secure lattice KEM in the standard model. This is a joint work with Xavier Boyen from QUT, Malika from CEA list. Let me first record key encapsulation mechanism, KEM for short. It consists of three algorithms. The key generation algorithm generates a pair of public key and private key. The key encapsulation algorithm takes as input the public key, and it generates a ciphertext C and a secret session key K. The decapsulation algorithm takes as input the private key SK, and it decapsulates the ciphertext C into a session key K, or it outputs error symbol. For standard correctness, we require that for honestly generated public key, private key, and ciphertext, the decapsulation algorithm correctly returns the encapsulated session key K with overwhelming probability. KEM is often used with data encapsulation mechanism to build a hybrid encryption. In terms of security of KEM, it is the standard requirement that the KEM should have adaptive choosing, should have a CCA2 security, which stands for indistinguishability against adaptive choosing ciphertext attack. So this definition consists of three phases. In the preparation phase, we generate the following things for the adversary. First, we generate the public key and private key. Then we choose a random bit value B, and we generate a real session key, key K1 star, using the encapsulation algorithm, along with a challenge ciphertext C star. We also choose a random session key K0 star, and the adversary obtains the public key PK, the challenge ciphertext C star, and the challenge session key KB star, where KB star comes from K0 star or K1 star, depending on the bit value B. In the attacking phase, the adversary sends over ciphertext C1 to CL, asking for decryption of them. The restriction here is that none of those chosen ciphertexts are the same as the challenge ciphertext C star. The challenger C replies the ciphertext query by running the decapsulation algorithm. Finally, in the guessing phase, the adversary outputs a bit value B star as a guess of B. It wins the game if B star equals B. We say a KEM scheme is CCA2 secure if the probability if the probability of successfully guessing the value B of the adversary is no better than 1/2. In terms of constructing CCA2 secure KEM from lattices, we have the following approaches. The first one is to apply the Fujisaki-Okamoto transformation to CPA's secure public key encryption. CPA stands for choosing plaintext attack. This gives us practical constructions, but the security argument can only be done in the random oracle model. The second approach is the Noyon paradigm, and it sometimes gives us less efficient constructions. The third one applies lossy trapdoor functions, but when it comes to lattice-based construction, the existing constructions require stronger lattice assumptions. The fourth approach, which is the one that we are taking, is to convert the CPA secure tag-based encryption using some generic transformation, for instance, strongly unforgeable one-time signature or strongly unforgeable one-time message authentication code. This approach gives constructions in the standard model, but the question here we want to address is how to avoid generic transformation in this type of construction. That is, we want to have a direct construction without resorting to the generic transformation. Our construction is a simple construction. Our contribution is the simple construction of CCA2 secure KEM whose security can be proven under the LWE assumption in the standard model. We don't rely on any generic transformation. And if in terms of efficiency, our construction is almost as efficient as the best known lattice public key encryption, but it only has CCA1 security. Let me record two computational assumptions that we make in our construction. The first one is the learning with errors assumption. The second one is the short integer solutions assumption. So let chi be a noise distribution over ZQ, and the LWE assumption says that it is computationally hard to distinguish between two distributions. The first distribution on the left-hand side consists of two parts. The first part is a randomly sampled matrix A, and the second part is S times A plus E, where S is the random vector and E is a vector sampled according to the noise distribution. The other distribution also consists of two parts. The left part is a random matrix A, and the right part is a random vector B sampled over ZQ. So computationally, those two distributions are indistinguishable. The short integer solution assumption says that giving a random matrix A sampled uniformly at random, and A is wide, then it is hard to find a non-zero no-norm vector E such that A times E is equivalent to vector 0 modulo Q. We also use the gadget trapdoor defined by Michangel and Peikert. So we define this matrix F, which is the concatenation of two parts. The left part is a random and wide matrix A, and the right part is A times R plus T times G, where R is a low-norm but sufficiently random matrix, and G is the gadget matrix. And T here is a square matrix. In the rest of talk, we will call it tag. So here, the interesting thing is that if T is of full rank, meaning that it is invertible over ZQ, then there is an efficient algorithm that can solve LWE by recovering the secret and the noise term. On the other hand, if T is 0, then this LWE sample is pseudorandom under the LWE assumption. Our construction is based on the efficient CCA1 public key encryption due to Michangel and Peikert. So let me quickly record this construction. So in this construction, the public key consists of two matrices, the matrix A, which is wide and random, and the matrix A1, which is a product of A and R, where R is a low-norm unpredictable matrix. To encrypt the message, the encryptor computes the LW sample Y equals S times A1 plus TG plus E0, E1. For a full rank tag T, the message M is encoded into the noise term E1, and the ciphertext essentially consists of two parts. The left part is the LW sample Y, and the right part is the tag T. For decryption, we can apply the gadget trapdoor to recover the terms S, E0, and E1 using the lattice trapdoor, and we can further recover the message from E1. Now let me quickly record the CCA1 security game. In the CCA1 security game, which is different from the CCA2 security game, requires that decryption query can only can only be asked before seeing the challenge ciphertext. And once the challenge ciphertext is given, no decryption query is allowed to made. So in terms of security of the CCA1 secure lattice public key encryption by Michancho-Picard, it is CCA1 security, and the idea of the proof is the following. So in the simulation, the challenge tag, which will be used for challenge ciphertext, is embedded in the public key matrix A1 from the very beginning. And because the matrix A is wide and R is sufficiently random, then A1 completely hides T star. So before seeing T star, the adversary has no idea what T star is. Then the decryption query made by the adversary will likely have the tag that is different from T star, so the decryption query can be answered. And when it comes to the challenge ciphertext, since T star has been embedded in the matrix A1, and when you apply T star to construct the ciphertext, the T star gets canceled out, and under the LWE assumption, this ciphertext is pseudo-random. So the CCA security crucially relies on that the decryption query before seeing the challenge tag T star will likely have the tag T that is different from T star, so the decryption queries can be answered. And on the other hand, it is not CCA2 secure, because in CCA2 security game, the attacker, after seeing the challenge ciphertext, can make a query by fixing the T star and changing the other part of ciphertext into another one, and that decryption query cannot be answered. So let me give you the ideas of our construction. By looking at the challenge ciphertext, the Y star, we can see that essentially we can answer all decryption query for any decryption query with the tag T that is not T star. This is also the case after the adversary seeing the challenge ciphertext, which has the tag T star. So what we want is that we want to bind Y star to T star, so that if adversary modifies Y star, it will have to modify the tag T star. So once the T star is different from, once the tag T star gets modified, we can apply our trapdoor to answer the decryption query. So our idea is to hash several items that uniquely determines Y star to get T star. And here, basically what we do is the hash of S times A plus the left part of noise E0, and also U times E1, where E1 is the right part of the noise and U is the newly randomly sampled white matrix. So by doing this, what we want is that since Y star is computed using S, E0, and E1, and A and U are public keys, so hopefully these terms will uniquely determine Y star. Now, if we look at what's inside the hash function, we have S times A plus E0, which uniquely binds S, A, and E0 in the information theoretic sense, because the matrix A is wide and E0 is the noise, which is small. On the other hand, we have another part, U times E1, which uniquely binds E1 computationally by the CIS assumption, because it is computationally hard to find another E1, another small E1 prime, such that U times E1 equals U times E1 prime. By doing this, we also want to make sure that T star contains no information about S, E0, and E1 so that we can apply the LWE assumption. For the left part, S times A plus E0, we can use the LWE assumption to argue that this term computationally hides S and E0. But how about the other term? We can see that U times E1, it by itself, information theoretically hides E1 because U is wide and E1 is sufficiently random. But however, we have another part which also contains the term E1. So we need to argue combining U times E1 and the other part that contains the term E1 do not leak any information about E1. So essentially here is abstraction. What we need to show is that the LWE term S times A plus E and the cis term U times E computationally hides E and S. So here it really looks like a cis instance is added to the LWE instance. Now the intuition, so intuitively this works because U is wide and E is sufficiently random. So ideally UE leaks little information about E, so it shouldn't help anyone to solve LWE. To justify this, we have a connection between the knapsack LWE and this cis plus LWE instance. So basically it says that if the knapsack LWE is hard, then S times A plus E, U times E is random, and in particular computationally leaks no information about the noise term E and the term S. So knapsack LWE assumption says that it is computationally infeasible to distinguish between two distributions. The first distribution consists of two parts. The left part is the random matrix A, which is wide, but not too wide. And the second part of the first distribution consists of the product of B and E, where E is a vector sampled according to the LWE noise distribution. On the other hand, the other distribution also consists of two parts. The left part of that distribution is a randomly sampled matrix B, and the right part of this distribution is the random vector H. So it's been proved that the knapsack LWE is equivalent to the LWE problem. In our proof, essentially we use some samples from the knapsack LWE to simulate the LWE samples S times A plus E, and the rest of them are just simply used as U times E. So now it comes to our final scheme. Basically, we only add one wide matrix to the CCA1 construction. So in our public key, it consists of three matrices, A, A1, and U, and the private key is R. Now to encrypt, what we do is that we sample S E0, E1, and we set S times A plus E0 and U times E1. Then we use these two terms to compute the tag T, and after that, we set the value Y. So this, and by the way, what we did, how do we encode the randomization key? We put it into the secret S, but we can also have other ways to do it. This is not really important. Anyway, the ciphertext now it still consists of two parts, Y and T. To decrypt, we just do the same thing. We have, since T is likely to be full rank, so we can apply the gadget trapdoor to recover the term S, E0 and E1. And the extra step we need to do is to check recompute the tag to see if it's consistent. If not, we reject. If yes, we recover the message from S or recover the session key from S. So to make a brief comparison, we only add one matrix to the public key, to the CCA1 scheme, that's all. And the ciphertext is just of the same size as the CCA1 secure scheme. And when it comes to the decryption, we need to recompute the tag, which takes a little bit more time. So in terms of LWE assumption, our LWE assumption has the same LWE modulo to noise ratio as the LWE assumption used by the CCA1 construction. However, we do need a little bit larger number of LWE samples in order to simulate the LWE sample and the knapsack LWE sample, the CIS part. Now, one may wonder why we can only do KEM, but not public key encryption. The thing is that, remember, in the security proof, we need to embed the challenge tag into the public key before giving out the public key. So that means the tag T star depends on the challenge messages. In KEM, the challenge message is just a random session key which can be chosen from very beginning. So we can embed the session key, the message, to the tag T to compute to construct the public key. However, in the public key CCA2 game, the challenge message is chosen by the adversary after seeing the public key. So this creates a difficulty. Our idea can be also extended to realize the full-fledged CCA2 public key encryption. How to do that? Essentially, we can fix T star first, and when we receive the challenge message, we choose the terms SE0, E1, and somehow hit the tag T star, so that we can still answer the decryption query before giving out the challenge ciphertext, and after giving the challenge ciphertext, since everything bounds together, that attacker cannot make any decryption query with the same tag T star. So now in the security proof, we're going to sample the matrix U along with a trapdoor using the GPV pre-sampling technique. So GPV pre-sampling technique says that giving a target U and the trapdoor, giving a target small u and the trapdoor for the capital U, we can sample the E1 such that U times E1 hits the small u. And concretely, we can do this, we can implement this idea using the lattice-based chameleon hash function to bind E1 S times A plus E0 together to hit the target tag T star. The question why we didn't use this for our KEM scheme, it's because if we do this by having a trapdoor for the matrix U, we need to require larger LWE modules to noise ratio, which is what we want to avoid. So in summary, in this work, we constructed a lattice KEM that is simple and direct in the sense that we don't use any generic transformation with one-time signatures or message authentication code, and we achieve adaptive chosen ciphertext security in the standard model. And our system is as efficient as the best known CCA1 lattice public key encryption in the standard model. And the technique we use here is to add a CIS function to hash the LWE noise term to make the LWE noise term non-malleable. Thank you.